Okay, welcome to the July CaTS webinar, sponsored by the Cyberinfrastructure Enhancement Core and brought to you with the Biostatistics and Epidemiology Core of the CaTS Center. Today we're going to be presenting a session by Dr. Robbie Beyl entitled "Not All Change Scores Are Equal." I'm going to hand that over to Dr. Beyl in a second, but first some introductions as to who are we. My name is David Alexander. I'm the core director for Cyber Infrastructure Enhancement. And with me, as I said, is Dr. Robbie Beyl. And not with us today, but who will be joining us in future webinars is Connie Merla, our RedCap administrator. And that being said, we have the chat room open. So if you have any questions, let us know. And we'll be happy to answer those either during or after the talk. So with no further ado, here is Dr. Beyl.
Thank you. So today we're going to talk about change scores. Again, not all change scores are equal, and we're going to focus on differences between relative versus percent change scores. So let's talk about the setup that we're going to use. Now again, this is not all the setups, but this is the one we particularly want to go into today. We're going to have a randomized clinical trial. We're going to have two treatment groups. We're going to call it treatment and control. We're going to have two measures, a measure at baseline and then a measure at follow-up. And one thing that's pretty unique about the example we're going to go through today is going to have a relatively small sample size. So in most randomized clinical trials, we usually have the hypothesis of, does treatment have an effect on the subject's response? With large sample sizes, mathematically, the two groups will be equal at baseline. They won't be exactly equal, but they'll be close enough. However, in small sample sizes, this won't always be the case. So we'll need to somehow adjust for these differences at baseline. We're going to go over a couple statistical methods to do that, but generally we're going to focus on how the hypothesis is going to now change to, does treatment have an effect on the subject's change in response? So there are going to be four total models we're going to talk about today. We're going to be talking about a full model, then the change score model, the follow-up adjusted model, and a percent change model. We're going to go through each of these and then go through some examples later to show you how they perform differently. So the first model we'll talk about is the full model. This is also called the ANOVA model. Here, we're going to retain the baseline value as one of the outcomes. So we're going to have two outcomes, one at baseline, one at follow-up. This allows for testing all different combinations of baseline, follow-up, and treatment groups. So we could test at baseline, are the two groups equal? At follow-up, are the two groups equal? Are the change scores equal? So this model is advantageous for all the different tests that we can use. It's best when we have multiple time points. Again, more than two is generally do we use this type of model, but we're just going to focus on two in here. And as well as when we have highly correlated data. This is a great model to use. The second model we're going to talk about are change score models. So here, we're going to remove that first time point from the analysis and subtract it off from each following time point. So if you look at the plots I have on the right, we can see that these two groups start at different time points and end at different points as well. But if we were subtracting off the baseline, we'd see these two groups actually follow kind of similar paths and then diverge at the end. So that's an example of how a change model would model the data. With that second figure, this model assumes that the baseline value does not affect the amount of change. So whether you start at 100 or whether you start at 200, the change should be the same because you're going to make those changes from baseline equal to 0. And these are generally best type of models to use when the baselines have different starting values, but again, is not affected by where they start at. The third type of model we're going to go over today is called a follow-up adjusted model. like previous, we're not going to use that baseline model as part of the response. But instead of subtracting it off like we did with model 2, in this model, we're going to use it as a covariate. So we can think of the model as the follow-up value equals treatment plus the baseline value. So we're adjusting for it. These models generally assume the baselines are equal, but accounts for differences across baseline. Overall, these are the simplest to understand because we can just say, adjusted for baseline, these are the results at the follow-up time point. This is also one step more advanced than just doing the analysis at the follow-up. So that's why these are the simplest models. The last model we'll talk about is the percent change model. So this is going to, again, remove that first time point and only model the follow-up time points after that. Instead of just subtracting off the baseline from the follow-up time point, we're then going to divide by that baseline as well. So one of the advantages to this percent change model is that there are no more units. Let's say we're measuring weight. We're no longer looking at weight change in pounds or kilograms. We'll look at their percent weight change. So did they gain 5% weight back? Did they gain 2% weight back? Instead of saying they gained 4 pounds back. So that's the advantage of here. It's unitless, so we can generalize it to a little more different areas. We also have to assume all the values are going to be positive. Strange things can happen if we have a negative in there, so we're just going to assume everything's positive. So like weight, they can still lose weight at the follow-up time point, but again, it has to be a positive weight. They can't weigh negative 4 pounds. These models are best when there are differences at baseline and the baseline has an effect on the response. So that's the little caveat that makes this one different than the chain score models. The chain score models, to reiterate, are not, we assume that they're not affected by the baseline value, but the percent change models we do assume are affected by that baseline value. So now that we've gone over all the models, what I'd like to do next is kind of run through a few examples of data and then what the different results show. Before I even go into this, the little caveat, these models produce different results, and none of these are necessarily the correct model to use, they're just different models. So again, no model is correct, they're just showing you different things because they all have slightly different assumptions and testing different things. So the general setup of the next couple slides will be, I'm going to describe the data in the top left corner, show you what the raw data looks like over time in the plot below it. On the right side, the top plot will show the means and what they're doing over time. And then the bottom table on the right side will be what model is showing a significant p-value for testing the hypothesis. So for this first one, we're going to assume the baselines are similar, and then the chain scores are different. So if we look at the plot on the left, we can see that the blue and the red lines all start about the same places. Some are high, some are low, but they're interspersed. And then they tend to change over time. Looking at the mean plot on the right side, we see again the means at baseline, time 1, are similar to each other. They're very close. We can see the blue group going up over time, where the red group is staying fairly constant over time. So if we were to run each of these 4 models that we previously discussed about, the full, the change score, the follow-up adjusted, and the percent change, all of them would actually come back saying there is a significant treatment effect. So that's an easy case where it shows it doesn't matter what model you choose, they're all going to have the same kind of conclusion. But let's go to the next step. Here, we're going to look at data where the baselines are different, but the chain scores are similar. So if you look at the plot on the left, we can see generally the red dots at time 1 are a little bit higher than the blue dots at time 1, but they're all trending upward. So looking at that mean plot on the other side, Again, those baselines are starting at different values, but they're kind of going up on the same trajectory. When we run all the models, the only model that actually comes back as significant here is the percent change model. The rest of these, I'll say treatment doesn't have an effect. And that's because they're starting at different baselines, and what assumption we want to make about it matters. So if we wanted to assume that the baseline does have an effect on the response, we should use that percent change, and we're saying it is significant. If we assume that that baseline doesn't really have an effect on the response, we set change model and say it's not significant. Okay. So the next set of examples we're going to look at are the baselines are different again, the changes are different, but now we have different directions. So if we look at that plot on the left side with all the data, we can see some red dots are going up over time, some are going down over time, and again, they're spread out everywhere. Where generally the blue dots are all consistently going up over time. If we use this model, we can see that the results show the change score and the percent change score do show significant differences in regards to treatment, but the full model and adjusted model do not. And that's because when you look at it, you can see that kind of at the follow-up time point, they're much closer in relation to than the beginning. That's why that full and that follow-up adjusted model are not picking up significant differences. Whereas that change score, whether it be percent change or regular change, we do see large differences there. That's why we're picking them up. So the next set of examples are baselines are similar, change scores are different, and the variation is different. And what I mean by that is the red line at baseline is spread out a good bit more than the blue. And when we look at the mean plot on the right, we can see that the standard error bars I have plotted at each time point, we can see the red are quite wide. So that's telling us we have lots of variation with it. So when we have the variation like this at the baseline, but not at the follow-up time points, again, you can see from that plot of the means that those follow-up time points are rather small standard error bars. Probably we want to focus on the follow-up adjusted model because that is going to help reduce overall variation and not focus as much as that baseline value. Here, we do, in the end, in this data, we see that the change score model and the follow-up adjusted model are significant. The other two are not. And again, not saying that those two are the right models to use, but that's we have to think about what assumptions we want to make. Okay. Now, I believe probably the last example that we're going to go over is going to have similar baselines, different changes, variation is different again, and directionality is different. So if we look on the individual plot on the bottom left, we see blues going down, blues going up, and there's a wide spread in the blue data. The red data is pretty consistent where it's just kind of going across, not a lot of changes there. So we see that if we were to look at the results from this model, we see that the full model and the follow-up adjusted model are the only ones showing significant. So again, this harkens back to if we have these large variations at baseline, we may want to focus on those full and follow-up adjusted models and not look at the change score as much because there's too much variation there. So now that we've gone through all the examples, I want to wrap it up a little bit and talk about what models are kind of better where and what you should generally do when you're thinking about the models, what to use. So we always want to look for baseline differences. If there are no differences, most of the adjustments will be similar. So it doesn't really matter what models we use. The second step would be to use the adjusted model if the baselines are equal. That's the simplest model to use. Most people understand that. That's just one step more advanced than a t-test at the second time point. So that's probably the best one to use if the baselines are equal. You want to use the full model to only consider one model for all tests. So if you're really interested in testing the baseline differences, testing within group changes for the treatment, within group changes for the control, and then change of change scores, then that's the full model. It gives you a wide range of tests. Most of these other models only give you one test. The change model is useful if the baselines are different, but you do not think the starting values are associated with change. So let's take weight, for example. If we know that the weights are different, but don't think that the starting weights are that different and should be associated with that much change, we should use a change model. However, the percent change score model is used when the baselines are different and the starting values are associated with change. So taking weight again, if we make some assumptions and say, we think a maybe 200-pound person will lose more weight than a 150-pound person, and we want to take that into account, we should use those percent change models and talk about how they lost 5% or 10% of their weight. And again, a good overall rule is to use these 4 different models all in the same data set and compare and think about what differences you're seeing and why. Help tell a story. So it's okay to look at all these different models, but generally in the end you want to choose one, whatever, again, helps you think tells the best story that you can tell with the data and explain the most. So I want to thank everybody for their time for listening. Again, here's a link to the core, and you can get some resources. We have additional tutorials on there. And again, thank you for your time.
Great, thanks, Robbie. That was fantastic. Great content. We don't have any questions in the chat session right now, so we'll go on ahead and wrap up for this month. But I just want to restate these links. If you have some ideas for topics you'd like to see in our webinar, please visit lacats.org/redcapfeedback. We have a RedCap survey there where you can give us feedback on any aspect of our webinar and submit ideas for future topics. We'd love to hear your feedback. If you're interested in training resources there, lacats.org/redcaptraining has lots of good videos and content about different features within RedCap. And if you think you'd like to try out RedCap, sort of kick the tires, there's a free 1-week demo at redcapdemo.vanderbilt.edu, and that will allow you to see what RedCap's capable of in a risk-free environment, so we highly recommend that. And that's it for this month. So thanks for joining us, and we'll see you again in August. Bye.
Bye.